Welcome back, everybody. So we're gonna be starting up a new section, just kind of giving you guys a little bit of an update for the class. So we're starting the next unit. So we're on to the last unit of our course, and we'll be taking our last test pretty soon-ish. You have your exam due your exam 3, which is due this Friday. You have 3 attempts. Please take it soon so that you can take multiple attempts. Just like usual, look over your answers, make sure everything works out right, and then if something's wrong, let me know. Otherwise, we'll go on our merry way on that one. We're not going to finish this section today, so there's no homework due this week for this one. But kind of giving you a rundown of what's going to be happening. So we're in the second week of November. We have next week, which is a normal week, and then the week after that is Thanksgiving week. I have deliberately designed it in such a way that we're going over material from chapter 5 that week, which is there's no homework on it. There's nothing tested upon it. There's nothing on the final quiz. There's nothing on the exam 4 on section 5, so that if you have to miss Thanksgiving week for whatever reason, if you're sick, or your goldfish got a cold, you have to be there to take care of it, that you don't have, like, there's no worries about missing a class during that week. What we are going over during that week is so I will be here on Monday and Wednesday, unless anything happens to me. And so I'll be teaching about voting theory, in particular ranked choice voting, which is what Nevada is switching over to. I mentioned very, very early in the semester, but Nevada is switching over to a ranked choice voting style for our elections, which is very, very good. It's a very, very good thing.
Is it this upcoming election?
I believe, I can't remember when it gets implemented. I think it is supposed to be for the next upcoming election. But we'll be talking about why it is, and my hope is that by watching those videos or attending class from that time, you're going to have the same thought that I did when I learned it, is why isn't this the way we do all of our elections? Why do we have to choose between two things that you don't necessarily even want? I don't understand why the choice is between two people who are above the age of, like, who will be over 80 if they are to obtain the presidency. Why can't I choose someone different? Either way, that's true regardless of your political affiliation. I don't think a person who is above the age of 80 should necessarily be making decisions for people who are like they're not going to be on the earth for much longer. My dad is 77, and I would not trust him to run the country, mostly because he has dementia. But that's a dark joke right there. It's okay. You can laugh. You can laugh. That's how I deal. That's how I deal with trauma right there.
Like your trauma.
Yes. But anyways, I'm getting sidetracked. So my hope is that by going over that stuff, you'll see, like, oh, this is actually a really good thing, and my vote, now your vote will matter more, and your vote actually counts. Whereas, like, if you're a person who is highly Democratic and you're living in a Republican state, there's no point in you voting, essentially, right? And vice versa. If you're a highly Republican person in a Democratic state, there's really not any point to you voting. You're not going to win. Local elections may be different, but, like, in terms of voting for the president, if you're living in Texas, it's probably unlikely that your vote is going, and you vote blue or whatever. It's going to be very unlikely that your vote matters. However, with ranked choice voting, it does matter. It does matter because you get to make the choice that you want, and we'll talk about it then later. Like, we don't have to talk about it now, but it is a very, very cool concept, and it's something where I really just don't understand why we don't do it now. Why isn't this just the way we do it? This is like the most fair way to run an election. So we'll get there. We're not there yet. So Chapter 4 is all about probability, one of the weirder areas of mathematics, in my opinion. Very, very strange stuff can occur. So that this title makes it seem like it's going to be very, very easy, right? Counting. I know how to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm good. Which that is not what the case is here. I had this book when I was preparing to study number theory in grad school. It said Elementary Theory of Numbers. The name of the book was Elementary, and this is how the book looks. Elementary Theory of Numbers. And it had a 1, a 2, a 3, a 0, a 5, and 9. It looked super colorful and cute. And I was like, I was reading it on the bus getting to campus. And I'm just self-conscious, like people saying, oh, look at that guy, he's learning how to count. And it's like, no, it's really difficult. This is number theory. Because number theory is a lot more than just counting. It's a lot more difficult than that. And so the questions in there, I'm sitting there getting stumped on it. And I'm feeling very self-conscious on the bus. But it is not counting like counting 1, 2, 3, 4, 5. So let's start off with what the counting is doing. So this section is on probability, and probability is figuring out the number of chances of success over the number of total chances. So like flipping a coin there's a 1 in 2 chance of getting a heads. There's one way you can get a heads, and there are 2 different options. So in order to talk about probability, we need to know how to find out the total number of possibilities. And that's what this is all about. So the fundamental counting principle. Fundamental counting principle. And we're going to talk about a motivation to start off with. By the way, as a total aside, so mathematicians, we use a bunch of different notation in different books. It's very frustrating. If you've ever seen the absolute value symbol, like this, that absolute value can mean 7 different things depending on the fields of mathematics that you're in. But one thing we do agree on is our structure on how we say theorems and stuff. Like there's a thing called a corollary, which is like a immediate consequence of a theorem. There's a lemma, which is a theorem that is not super as important as the theorem, but it's still important. And then there is what is it? Corollary, a lemma, there's a postulate, there's a bunch of different things. And then there's one thing that is consistent throughout every field of mathematics, is that we only reserve the name fundamental for something if we think that it is truly fundamental to the entire subject. So in algebra, there is the fundamental theorem of algebra. In number theory, there's the fundamental theorem of arithmetic. In calculus, there's the fundamental theorem of calculus. And for probability, there's the fundamental counting principle. So that's to tell you that this is a very, very important thing in how probability is formed. So the motivation for this principle is how many outcomes are possible from flipping a coin 3 times. Now, you might know the answer already. You might not. And how would we go about finding it? There is one way that's the most logical way, but much more tedious. The first way would be brute force. Right? We could say, okay, you could either get heads, heads, heads. You get heads, heads, tails. You could get heads, tails, heads, or you could get heads, tails, tails. Those are all the situations where you start off with the heads for your first flip. Then you could get tails, tails, tails. You get tails, tails, heads, tails, heads, tails, or tails, heads, heads. Those are all the situations. How long it takes you to figure out all the different options, that's not important because there's a faster way. But that would be one way. But this is not very there's plenty of chances where you might forget something. You might forget one of the options when you're trying to count them. Or if this was like 5, right? Heads, 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 tails, heads, 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 tails, heads, and so on and so forth. It would take forever to write them all down. There's got to be a faster way. Must be a simpler way. So I'm going to put 3 bars here. Say first flip, second flip, and third flip. How many possibilities are available for my first flip? 2. I could flip a heads, I could flip a tails. 2 possibilities. Same thing for the second flip, and same thing for the third flip. It's not like I changed the coin. I didn't change the coin or anything like that. Same coin, so there's 2 outcomes for each of them. And then if I multiply these all together, I get 2 cubed, right? Which is 8, which is precisely how many I found in the first option. If you count it up, there's 8 options here. There's 8 choices in the brute force method, and then just doing 2 times 2 times 2, multiplying all the outcomes of each flip together gave me 8 as well. And the question would be, is this a fluke? Like, does this only work with coin flips, or is this true in general? Like, what if I rolled a D20, a 20-sided dice, right? What would be the options if I rolled the dice 3 times? What would I get? And could I just do 20 times 20 times 20? And the answer is yes. And so that's the fundamental counting principle. I'm recording, right? Okay, good. The fundamental counting principle says that the total number of options/outcomes of a multi-part event is determined by multiplying the number of choices for each event together. Let's write that down before I go onward. So if you want to know the total number of options of a multi-part event, so the coin flips is a multi-part event. There's 3 events. There's a first coin flip, a second coin flip, and a third coin flip. And the question is how so that's a multi-part event, and it's determined by multiplying the number of choices for each event together. First event had 2 options, heads or tails. Second event had 2 options, heads or tails. Third event had 2 options, heads or tails. Multiply them all together, you get total number, which is 8. So let's look at an example, and then we'll talk about why it works. And so to preface this example, up until I moved here for this job, I really only taught STEM-based courses. So I was only teaching like calculus or business calculus. I was teaching business calculus as well. So I was in the business department sometimes. But business calculus, business algebra, pre-calculus 2, all those things. And I never taught liberal arts mathematics such as this course. So when I was creating my notes for the semester, I was on the North Las Vegas campus, and maybe you've had this instructor before, but Arnold Bell, does that name ring a bell? He's an instructor with the comm department, very nice man, very kind, very well spoken. But one of the things that is very noticeable about him when you meet him is he's very dapper. He is very well dressed. And so like I had noticed it every single time I talked to him between classes. He was always wearing a different suit. Always wearing a different suit. And I kind of talked to him about it. So I was wondering, like you're wearing a different suit. And so his statement was that when he got this job at CSN, every paycheck for the first several few paychecks, he would always buy a suit. It's like because this was his big boy job. And he wanted to look the part and show professionalism. Love the concept. And it just so happened to create this example for the class. So, example. Arnold has 7 ties, 10 shirts, 4 pants, and 4 suit jackets. How many outfits are possible? Now, of course, like if you're wearing I remember him wearing a pink suit at one point, and if he has a lime green tie or whatever, that's not really going to be a good outfit, but it is an outfit. So how many different ways? So the thought that I had was like, I wonder how, based on how many things he has, how many different, would it be possible for him to go to every single one of his classes and always be wearing a different suit and tie, like a suit combo? And so that's where this problem comes from. So and this is not that many, right? 7 ties. I'm getting a tie every Father's Day. So once my kid is 7, I've already got 7 ties. If this is an easily obtainable amount. So how many outfits are possible? Well, solution. So you have your tie options. This is a multi-part event. The first event is choosing your tie. The second event is choosing your shirt. Third event, choosing your pants. And fourth is choosing your suit jacket, or just jacket. So there's 7 ties times the shirts, of which there are 10, times the pants, of which there are 4, times the jackets, of which there are 4. And if you plug this into 7 times 10 times 4 times 4, that ends up being 1,120 outfits. That's how many outfits you can make. You're wondering, you don't want to know how many outfits you can make. True. Once again, this is assuming maybe I don't think it would be a wise idea to wear horizontal striped shirt with a vertical striped jacket. I think that would look a little bit wonky, but you could do it. You could do it. And so now we know that, so he meets his students 3 times a week for 15 weeks. That's 45 classes. So 45 divided into 1,120 divided by 45. He could be good for 24 semesters before having to repeat an outfit. Now, but I have certain preferences. I have a tie that I absolutely despise, but I will wear it on occasion. So, I mean, this isn't 100% accurate, but you could have up to 1,120 outfits just by having 7 ties, 10 shirts, 4 pants, and 4 suit jackets. So, the question though is, why does this work? Why does the fundamental counting principle work? Because you told me to.
That's exactly the answer.
I don't know if I told you. So one of my, I used to, my first semester here, I taught at the high school, Palo Verde High School in the CSN satellite campus as well. And as I was getting out of class, because they only have a night classes, and there was a grandmother with her grandson, and they were just getting out of like a little workshop or something, and the kid came up to him, like he noticed that I was carrying a bunch of books. And he said, "What are you doing?" He was like, "I'm a teacher." And he said, "Do you know how to do long division?" And I said, "Yes, I do." And he proceeded to tell me how to do long division. And we were very, very cute. And and the teacher brain wasn't off yet. So I said, "And do you know why that works?" And he said, "Because my teacher told me to." And I love that answer. So it just makes me think of Patrick going, "Because you told me to." And so, but the actual reason why it works, let's talk about it. So the formal proof of why the fundamental counting principle works is a lot hard. It's a lot more mathy than we're privy to. There's a lot more formal mathematical knowledge that we don't have in this course. But we can look at this as a specific example to extrapolate the idea. So imagine, let's just assume, like me personally, if I'm trying to pick out a suit combination, I usually pick out the suit first, then the pants, then the shirt, or like the suit, then the shirt, then the pants, then the ties. But let's just assume we're going down this list as it stands. So he first picks out his tie. So when he's doing that, he has 7 choices. He has tie number 1, of which once he picks that, he's now going to pick a shirt. And there's 10 different shirts. He could pick shirt number 1 all the way down to shirt number 10. And then he does this for every one of his ties. That's one tie option. He could do it for tie number 2, tie number 3, tie number 4, all the way to tie number 7. And when he picks tie number 7, there's 10 options for shirts. Shirt 1, all the way down to shirt number 10. Like, think about these as parallel universes, right? In one situation, he picks tie number 1, and then he looks to see which shirt he should take. And then in a parallel universe, he's at number 7. He picks tie number 7, and then he picks another shirt. That is 7 sets of 10, right? Because each one of these would be a tie and shirt combo. So this is 7 sets of 10, which is 7 times 10, which is 70 shirt combos. Sorry, shirt and tie combos. $70 shirt and tie combinations, 70 of them just from that. So that gives, so now there's 70 parallel universes. In parallel universe number 40, he picks tie number 3 and shirt number 7. And so in that universe, he now moves on to his pants. So now we have a shirt and tie combo. Shirt and tie combo number 1. And now he has 4 different pant options. Pant number 1, all the way down to pant number 4. And we do this for all 70 of the shirt and tie combinations. So shirt and tie combo number 70. Once again, you can choose between pant number 1 all the way down to pant number 4. And so that is 70 sets of 4. The first set, the first shirt and tie combo, choosing tie number 1 and shirt number 1. You could choose pant number 1, pant number 2, and pant number 3 or pant number 4. There's 4 options for each one of the sets, of which there are 70. So that's 70 sets of 4, which is 70 times 4, or more aptly, 7 times 10 times 4, which is 280 shirt tie, and pant combos. And then we can say, etc. Do you see the pattern that's going on here? We can just keep going on to the next one. We get more and more parallel universes each time. So that's the reason why it works. Each option gives you so many new options from everything. So one of the other ways that some people write it is they say, okay, so your choice, here's pant number, here's tie number one. You don't need to write this one. Tie number one, tie number two, all the way to number 7. And then each one of these things has shirt number 1, 10, 1 to 10, 1 to 10. And then each one of those things branches off into a new thing. And then you just count all the ones at the end, but that's all just based on multiplication. That's why the fundamental counting principle works, which is pretty cool. So that's why it works in a specific example, but the process is going to be the same regardless of what this was. I could have said, I could have said, well, we can even do that example in a second, but it doesn't have to be shirt, tie, and pant and dress suit. It could be any of those things. So let's look at an example, another one. Now that we know how the fundamental counting principle works. So example, a 5-digit security code is it consists of 3 numbers, 0 to 9, and 2 letters, A through Z. Access to some security, like some important documents or whatever, what really happened at Area 51, who really shot JFK, all those things. So that this is the 5-digit security code. Question A is, how many possible codes with repetition? B is how many codes without repetition? And part C is going to be not it's not a question that you'll see on your homework or quizzes or anything like that, or anything in this course. I just thought it was a fun question to bring up a cool topic. So suppose, I'll let you write those down first. Suppose a computer, suppose a hacking program can test a code every 5 seconds. How long until the program, how many hours? How many hours? Sorry. How many hours until the program tests every code in part A? We'll get to that one in a second, but so question C says, suppose a hacking program can test a code every 5 seconds. How many hours until the program tests every code in part A? Because part A and part B are going to have different answers, and I just want to do it with part A. All right. silly little pop quiz. How many numbers are between 0 and 9? 10.
Oh.
So if it's the numbers 1 through 9, that is 9 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. But if it's 0 to 9, that is an extra number that makes it 10 numbers. It's okay. It was a pop quiz. As soon as you hear pop quiz, blood starts like blood pressure starts getting up there, getting nervous. It's totally understandable. I mean, I once again, you're talking to the person who didn't realize that was why it was called a triangle until grad school.
What?
My senior year math teacher used to pop quiz all the time, and I was like, wow.
You don't like pop quizzes? Yeah, I didn't like pop quizzes either, but
Like, no, you used to pop test, like,
no.
it was insane.
So with be careful in the verbiage with repetition. That means that the code 000AA is possible in part A. But without repetition means that none of the numbers can be used ever again. So with part B, 001AA, or sorry, 001AB is not possible because the 0 got repeated. So let's do this by using the fundamental counting principle. So every digit in the code is a new event. So solution. Part A. For the first digit, we have, so first digit, second digit, and third digit. Because repetition is allowed, there is no limiting factors. We can use the same digits over and over again. So each one of these is going to be 10. 10 times 10 times 10. And then for the third digit, the fourth digit, it's a letter. You guys know how many letters there are in the alphabet?
26.
There we go, 26. And then for the fifth digit, the same thing, because repetition is allowed. You can have 000AA. That's how many codes options there are. We'll put this into our calculator. 10 cubed times 26 squared is 676,000. That's just a 5-digit code. And that it becomes a lot larger when you start adding in letters. And this could even be, if it said any letter or number combination for each one, then there's 36 choices, right? Because you could have a 0 up to 9 or A, B, C, or D or whatever. So that would be a much larger color combination, but this one's in this specific pattern of 3 numbers and 2 letters. Much like license plates, right? I'm pretty sure every license plate in Nevada is a 3-digit number and then a letter and then 2 digits, right? Don't tell me your license plate number. I don't need to know that. I don't need to cause any stalker issues here. But that's kind of like, you can find out how many different possible car license plates there are based on that. So that is part A. That is using the fundamental counting principle. Part B. It's the same thing. It's 5 digits. Your first digit is a number between 0 and 9. There are 10 options. But now, in the choice of the second digit, we cannot use the first digit we chose. So now there are only 9 options. And then continue onward. Now we've used 2 of the numbers out of the 10 total numbers. So there's 8 left. Then for the number for the letter portion, there are 26 choices for the first one, but now that we've used one of the letters, there are only 25 available for the second choice. And that will end up being 468,000. So by making that small requirement that you have to, you cannot repeat anything, you limit your options by about 20,000. Still, 468,000 is still a lot of choices, but either way. Does that make sense? Does there any questions on that? So be on the lookout for if it says with repetition or without repetition. That does play an important role. Now, part C, once again, this is not something you're going to be tested upon, but I thought it was a fun problem. So it's dimensional analysis. Right? It said that it can go through one code every 5 seconds. That is a unit rate or a unit fraction, right? If you remember that terminology, that's a rate. One code every 5 seconds. We start off with, in part A, we have 676,000 codes. And then what we're going to do is he can go through one code every 5 seconds. And that'll cancel the codes and give us seconds, but I want hours. So I can either do the conversion that there are 3,600 seconds in 1 hour, which I don't know why you would have that memorized. I would prefer to convert it to from seconds to minutes and then from minutes to hours. So there's 60 seconds in 1 minute, and the seconds will cancel. And then there are 60 minutes in 1 hour. And the minutes will cancel, and we'll be left with our answer, which will be in hours, which is exactly what we want. And if you plug this into your calculator, you will get exactly 938.89 hours, which is equivalent to roughly 39 days. Straight, that is. So this computer program doesn't go to the bathroom at all. It doesn't take a nap. It goes on for 39 days until it finally tests every single data option. Now, this isn't exactly how code breaking works in modern day, by the way, in case you're curious. If you've ever wondered like how you can send your bank account information, your routing number and your bank account number through a check, and get that sent through the air, which is crazy enough as it is. Like if we don't marvel at the internet of just a bunch of ones and zeros being sent through the air and then magically showing up on my screen, that is fascinating. But anyways, someone can intercept that information and like, how do they make sure that's protected? That has to do with number theory, in particular prime numbers. So what they do, or what they used to do, is they would use they would pick a random prime number as a deciphering tool. It was like the key to a code. And so if you had the key, you could unlock the code. But if you didn't know the key, which if you didn't know the prime number, you wouldn't be able to figure out the code. And so they would use prime numbers, specifically very, very large ones. And there's a fact in mathematics is that there are infinitely many prime numbers. So 3, 5, 7, or 2, 3, 5, 7, 9, or sorry, 2, 3, 5, 7, 11, 13, and so on and so forth. You can go on and on forever. And so we found a lot of prime numbers, but computers have become incredibly quick and efficient at testing them. So mathematicians nowadays are trying to find ways to encrypt data better than that in ways that a computer could not handle. But now with the creation of like ChatGPT and all that stuff, maybe that's going out the window as well. But very, very fascinating. So I thought this was a cool problem. It doesn't exactly do this, but that's how it would do it. Essentially, it would keep testing different prime numbers until it found the right one. So pretty cool. Not going to be tested on though. Question A and B, fair game. Question C, not fair game. Any questions on A and B particularly? All right. And this is how you can become really, really popular with your friends if you guys ever go out to eat at an ice cream shop. So an ice cream shop. I don't know what distinguishes a shop versus a shop.
Well,
but-
it sounds cool.
Like what makes my ice cream shop a shop? I know it's pronounced shop, but otherwise I need to add that little extra, a little tilde at the end. So an ice cream shop has 31 flavors. This isn't based on anybody at all. An ice cream shop has 31 flavors of ice cream,
I just wrote.
4 different cone options. So like they got the regular cone, like the sugar cone. They've got a waffle cone, a waffled chocolate dipped waffle cone with sprinkles, and a chocolate dipped waffle cone.
Don't have the bowl though, I think.
I mean, like plenty of places do. Some of them have a waffle bowl, but and 5 different toppings. They got that marshmallow fluff. They got that caramel, that hot fudge, and strawberries at 4, I think, and then peanuts, crushed peanuts. Good enough. A special, quote unquote, consists of of 2 scoops on a cone with a topping. How many specials are there? So, just by requiring 2 scoops of ice cream at this place, I mean, granted, you don't really want to be mixing the sherbet with the dark chocolate or the almond toffee type thing. I mean, you could. I don't think it would taste very good, but you could. So strawberry sherbet with mint chocolate chip and peanuts. You could do it, but it wouldn't be good. So, how many specials are there? Solution is a fundamental counting principle. You have your first scoop, of which there are 31 flavors. Now, it didn't say that you couldn't choose the same flavor twice. So you could do 2 scoops of vanilla or 2 scoops of almond ripple fudge or whatever they call them. So you could do 31 for your second, like there's 31 options for your second scoop as well. Then you have a cone option, of which there are 4 different choices. And then you have a topping, of which there are 5. And if you do that, if you multiply those things all out, so that's all it is, 31 times 31 times 4 times 5, you should get 19,220 options. Boom. So that's what you should do with your friends next time you guys go out to the to an ice cream shop together. Go as soon as you're about to eat your ice cream, say, "Hold on, everybody. Let's find out how many different things are possible." And that's a surefire way to open up a very, very productive discussion with your friends. What? There's nothing wrong with being a nerd, but nerds do make money. If they don't want to figure this out with me, then they're no friends of mine. Like this is a Friday night at the cookhouse. So you can do this legitimately. Next time you go to Cold Stone, look at how many toppings there are. They got the Kit Kats, they got the Twixes or whatever. Find out. Never do the Twix, by the way. Never do the Twix. The caramel becomes rock hard and becomes inedible. So don't do it. Don't do it. Learn from my mistakes.
Thanks.
Thank you.
So that's how many options there would be in this situation. Fun fact. All right. Now we're going to start talking about permutations in a second and combinations, but in order to talk about them, we do need to talk about a very cool math concept, which are factorials. Has anybody heard of a factorial? If you have, awesome. If you haven't, not a big deal. They're surprisingly common. It's fascinating how often. So let n be an integer integer greater than or equal to 0. So once again, this is going to be a very mathy definition because it's talking about a general number for any number. That's the reason why it's going to look so intimidating. But once you see it in action, like, oh, okay, I see what it is. So let n be an integer number greater than or equal to 0. Then the factorial which is denoted n exclamation point, is defined by n factorial is equal to n times n minus 1 times n minus 2 times ... times 3 times 2 times 1. So that formula makes it look really intense. All it is you take the number that you're given and you multiply down the line. So you multiply, once you write it down, I'll give you an example. And then what's really, really, really cool is later on in mathematics, there's a function called the gamma function and the beta function. And they just so happen are able to compute factorials for anything. And so they even can compute factorials for half numbers, which is very strange, very, very strange. What is 1/2 factorial? You can't compute it by this means. Can't do it. But with higher division mathematics, you can, which is pretty cool. And there's one extra thing with 0 factorial equaling 1 by necessity. So we created this concept, like humans created this concept, so we get to do whatever we want. And in particular, we said that 0 factorial has to equal 1. I know that seems kind of weird, right? Because 0 factorial, you would think it would be 0, but it honestly, it comes about because of necessity in a lot of different theorems and formulas that we have that involve the factorial, and how they would become much more annoying to write if we made it so that 0 factorial equals 0. Whereas if we make 0 factorial equal to 1, it makes everything look nice and pretty. That's the reason why 0 factorial is 1. There are intuitions as to why it would be true, but in general, it is found out this way by the fact that it's just by necessity. So as an example, to make it make more sense, an example. 5 factorial is 5 times 4 times 3 times 2 times 1. That's all it is. So that's 120. And 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is going to be 720. And then if I decide just to give you one that's pretty crazy, 52 factorial. It's 52 times 51 times ... times 3 times 2 times 1, which if you plug that into your calculator, it will give you the beautiful number that is 8.0658 times 10 to the 67th. That is a number with 68 digits. For context, a million is 7 digits. A trillion, I believe, is 12 digits. Let me see. So
this is 67.
this is 68 digits. Yeah.
Oh, that's great.
Why did I pick 52? Is there something we know of that has 52 things in it? Come on, my Vegas people. What thing do we know of that has 52 things in it? Roulette has, I think, 30, right? But you're very close. A deck of cards.
Oh.
A deck of cards has
You're so
52 cards in it. And so, there was a thing. So back to, so you're saying that like that type of a question was a typical thing in the Cook household every Friday night. One day I was reading on a Reddit thread, someone trying to show you the size of 52 factorial. And I didn't believe it. So I went through on my Friday night to figure out if it was true. And it is. Now I'm going to butcher it a little bit because I don't remember exactly everything, but to show you how big. So first off, here's one thing for context. The moon is 1.3 times 10 to the 9 feet away. That's how far away the moon is. That's a 10-digit number. This number, 52 factorial, has 58 more 58 more digits.
That's wild.
So the way someone described it is, how big is 52 factorial seconds? So count seconds until you count each second until you reach a billion. So, or until you reach a billion years. After 1 billion years, take one step. Then count another seconds until you reach a billion years. Then take another step. Another billion years, take another step. Once you've walked all the way across the earth, take one drop of water out of the ocean. Then repeat that process. One step every billion years, take another step, billion years, take another step until you reach all the way around the earth, then take out another drop. Once you've done that a bunch of times and you've emptied out all the water in the oceans, fill the water back up, put one sheet of paper down, and then repeat that process. So every billion years, take another step. Every billion years, take another step until you reach all the way around. Take out one drop of water until you finally take out all the water, refill it, put up another sheet of paper. Once that sheet of paper reaches the moon, you still have, I think, 15 more digits. That's how long that number is. So like you can probably look it up. How big is 52 factorial Reddit? And it'll probably show up. And there's I'm probably a little bit wrong on my numbers, but that's the idea. That's the size of it. The point being, there is no way, shape or form, there's no way, no how that you and I will ever see the same deck of cards in our lifetime. So like every card game that has ever been played, there has never been the same set of cards. Every single game that's played here in Vegas every day, a different set of cards. It's possible for you to have the same set for like 3 or 4 of them, right? But the chances of you and me picking up a random deck of cards and playing War, and us playing the first thing and then having to play 3 more and then being the same thing and then playing 3 more, if you've ever played War before, it's impossible. So it's just never going to happen in our lifetimes. We're never going to see the same set of cards ever, which I think is pretty cool. So the other thing I wanted to mention about these things, just because this is a really fun mathematical concept and I love it. Notice that just by increasing the number by 1 here, going from 5 to 6, we've gone up by 600 numbers. 7 factorial. Going up 1 more number is 5,040. So just by going up 1 number again, now we're over 4,000 larger than it. And then going up 1 more number, we're now at 40,000. So we're 36,000 numbers bigger than it. So this thing grows incredibly fast. The factorial is one of the fastest growing concepts we've created. And then mathematicians have decided to go a little bit ham on it. And they created a thing called the hyperfactorial, which is you write two, you don't need to write this down, but 5 and then 2 exclamation points. And the way that is written is that it's 5 to the 5th times 4 to the 4th times 3 to the 3rd times 2 to the 2nd times 1 to the 1st. And that number grows even faster, as you could imagine. 5 hyperfactorial is, let's do it. So 5 hyperfactorial is 86 million. So just by being the 5th hyperfactorial, you're already in the millions, in the 100 millions. 10 million. Yeah. Wouldn't that be great? Like someone accidentally puts an exclamation point in your number. And then, oops.
Whoopsie.
So, any questions on factorials?
I believe, for the moon factorials, like, how did they know the first number for factorial?
So that one was just found out by doing other calculus, doing other mathematics. And so that what we see there, right there, that 1.3 times 10 to the 9th, that is what we call scientific notation. And it's a way to represent very, very large numbers in approachable terms. Like, I don't want to write out 67 digits, right? So that's what that is. So that wasn't the moon distance wasn't calculated by factorials. That was calculated by some physics and calculus calculations. But how they figured it out is a good question. I'm not quite sure. I'm not a rocket scientist. Obviously, they didn't have someone walk to the moon. That's impossible. But yes. So it depends on your calculator. Everyone's a little bit different. Mine, let me see here. It's been a while since I've had to use it. It should be most calculators, if they have a factorial button, it says X with an exclamation point. So mine, if you have my calculator, there's a button that says X to the -1, and then above that in yellow, it says X exclamation point. So did you find it? Yeah. Okay. So yeah, you can use that, but we're actually going to be we're not really going to be computing too many factorials because there's a button that we're going to use for combinations and permutations. So let's talk about permutations. So definition. A permutation is an arrangement of distinct objects in a that are placed in a specific order. So it's an arrangement of distinct objects that are placed in a specific order. And so with permutations, order matters. That's what's important. Combinations, which we'll talk about next after this, combinations order does not matter, but with permutations, order does matter. So an example of a permutation would be like trying to see how many possible ways you can have a like in a committee, if there's different roles like a treasury, a secretary, and a president, right? Figuring out the number of ways that the president, secretary, and treasury can be defined requires order, because you being the president is much different than you being the treasurer. That is an example of where order matters. Or this example that I have here after I write the formula is an example of permutation. We'll see it in a second. So the formula for it. The number of permutations of quote unquote n objects taken quote unquote r at a time is given by NPR, and lowercase n, capital P, lowercase r, equals n factorial divided by n minus r factorial. Now your calculator has a button for this. No matter what calculator you have, if you need help finding it, let me know. If you have my Casio calculator, the NPR and NCR buttons are found on the multiplication by pressing shift to activate the yellow stuff. and going to the multiplication or the division symbol. That's where my NPR and NCR are. So you don't actually have to calculate it, your calculator can calculate it for you, which is nice. But I wanted to talk about how the formula came to be, and that's why we talked about the factorials. So I realized, though, that verbiage looks very, very strange, and I want to talk about it. That is the formula, and your calculator should have a button for it. I really recommend before taking the quiz or doing the homework, you find out that button. Like when you're doing the homework, try and find that button so you can do this quickly. So as an example of a permutation, in a race of 15 people, how many different ways can first, second, and third place be awarded? How many different ways can first, second, and third place be awarded? So that n objects taken r at a time really feels weird when you first read it, but once you see this in action, you're like, oh, okay, I see what that means. I see what they're saying there. It's weird, but I get it. So now granted, we're learning about permutations right now, so of course this is going to be a permutation problem. However, we learn about permutations and combinations in the same section. So your homework assignment, it's not going to tell you which one to use. Your quiz is not going to tell you which one to use. So you need to be able to distinguish between the two. So if you looked at the calendar, I'm dedicating 2 days to this topic, to 4.2. Today, we're going to be going over permutations and combinations, and then and maybe finishing up a little bit of that on Monday, but primarily on Monday is going to be a bunch of examples that we're going to look at and try and determine which one we should use where. So you're prepared for the quiz and for the exam, for the homework and for the exam when we get to that. So when you're looking at a problem such as this, you want to ask yourself every single time, does order matter? So, and you could do this by like making up a scenario in your head. If we have runners A, B, and C, so first, second, and third place. Is runner A getting first, B getting second, C getting third? Is that the same thing as runner C getting first, runner A getting first, or sorry, A getting second, and runner B getting third? Are those the same situation? No, you getting first place and you getting second place is different, right? Order matters here. An example of where order wouldn't matter is, if I'm getting hungry, at a Mexican restaurant with a combination plate, right? My favorite type of thing. That's what I always get. If I get a taco, a burrito, and an enchilada, that's the same thing as getting an enchilada, a taco, and a burrito. The only thing that's gonna be like, it doesn't matter. Like I can eat them in any order I want, and it's not like it changes based on whether I say it one way or the other. So order matters here. Getting first place and second place are two different outcomes. So order matters. Order matters here. Getting first is different than getting second place. Order matters in this situation. So this is a permutation. It's a permutation of 15 people taken 3 at a time. So n is 15, r is 3. So the n value is the total number of things in your event or in your situation, and r is the number of things you're looking at in particular, the order of the things that you're arranging. So that's what they mean by n objects taken r at a time. 15 objects, people in this case, taken 3 at a time. Yeah, people are objects, I know. But like in mathematics, they think like that's what the object is in this scenario. So that's what the n objects taken r at a time is saying. 15 people taken 3 at a time because we're looking at the first, second, and third place. So we do 15 P3. And when you enter that into your calculator, pretty much all of them are done the same way. You have to put in the first number first, then press the button, then press the right number. So if I do 15, then do shift multiplication symbol to get the P, and then put 3, I get the exact amount, which is 2,730. There are 2,730 different ways for there to be a first place, second place, and third place winner. That is yes.
What does it mean by how many different ways can first, second?
So like how many different ways can the run so you don't know who's going to win the race. So how many different ways can first place be awarded, second place be awarded, and third place be awarded? Yeah. So like you could have runner A get first place, runner B get second, runner C get third place, or you could get runner D getting first place, and so on and so forth. Yeah. So we will be doing plenty of examples tomorrow, or not tomorrow, next week on Monday. So don't worry about that too much. We're going to just continue going on, and we're talking about combinations now. So combinations. So definition. A combination is a collection, just like a permutation, is a collection of distinct elements in which order does not matter. Think about like an example of this. I mean, you may disagree depending on your trauma with these types of games, but like getting picked for handball, right? Technically speaking, it doesn't matter if you're picked first or picked last. The team components are still the same, right? If I got picked first or I got picked last, no matter what, I'm still in the group. It doesn't matter. Like if there's different positions in the game, right? Like soccer or whatever, then there's something different. But with with dodgeball, we all have the same position. We're all just throwing the ball. There's no defender or whatever. So in that situation, yes, it feels bad to be picked last, I guess. But you being picked first or being picked last doesn't actually change the outcome of your team. It doesn't change the order of your team because they're all doing the same thing. And the other example is, once again, the taco, like the combination plate in a Mexican restaurant. Getting a taco burrito and enchilada is the same thing as an enchilada burrito taco. It doesn't matter which one you pick first, they're the same thing. And the formula for it is that the number of combinations of n objects taken r at a time is given by, instead of NPR, it's NCR, and it's equal to n factorial divided by n minus r factorial times r factorial. I'll let you write that down before I talk about it in detail. I want you to notice the similarity between the NPR formula and NCR formula. The NPR formula, the permutation formula, is just this portion. So the combination formula just has an extra factor in the denominator. It has that r factorial. And that's because like we can go, like, if we wanted to, we could talk about all day talking about why the formula is the way it is and how it works. But in essence, if you want to know the reasoning behind why that r is there, is to kind of basically cancel out any of the same things that happen. So the n factorial times the over the n minus r factorial, that gives you all the different combinations. That gives you, like, writing it down just once again so we can see it in action. That gives you the taco burrito enchilada and also the enchilada taco burrito. And what the r factorial does in the denominator is it basically sees both of those situations and cancels them out. And that's what that r factorial is doing, is it's basically taking care of all the redundancies because order doesn't matter. What about the bet? True. That's just an example. You don't need to write that on our page. So that's the formula. I've got you an example, and then we'll call it good for the day. So if there are 15 people in an HOA, how many different ways can a 6-member subcommittee be selected? That verbiage is very, very strange, but selected is important. You'll see it in our, like, once we talk about it on Monday, that trying to distinguish what thing is a permutation and what thing is a combination. There's usually key verbiage that you can look out for instead of asking yourself, like, you can bypass the asking yourself if order matters by looking out for some key verbiage. If you see arrangement or order in a problem, that's usually that's almost 99 times out of 100, that's a permutation problem. Where if it says selected or chosen or choose, that's a combination problem. We'll write that later on. We'll write that on Monday when we're talking about it. But this is a situation. This is going to be a combination. Order doesn't matter here. This subcommittee is just forming. So maybe later on they'll decide upon a chair of the like a chairperson. They'll decide on like a treasurer or a secretary or a note taker or whatever. But as it stands, we're just selecting 6 people to be on this committee, this subcommittee. So there's no different positions. So it doesn't matter if I'm picked first or picked last. Does that make sense? Why order does not matter here? If it said that there was like how many different ways can a chair, a treasurer, and a blah 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 person be chosen, then order matters, because being a chairperson would be different than being a secretary. But as it stands, there's no mention of that, so this is going to be just 5 or 6 people being chosen for a committee. So this is going to be 15 people taken 6 at a time. So that's going to be 15C6. Which, if you plug that into your calculator, 15, then press the NCR button, and then 6, there's 5,005 ways. Pretty crazy. That even with 15 people, just 15, We have, I think, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We're missing one person. So, and a ghost.
Roger.
If we wanted to pick a 6-person group from this class, there'd be 5,005 different ways to do so. It's pretty crazy. So that'll do it for today. We'll pick up next time with a bunch of practice problems to be able to distinguish between permutations and combinations. So that'll be it. If you have any questions, feel free to email me. Otherwise, you guys have a great day, a great weekend. I'll see you guys on Monday. Please make sure you take that test as soon as possible and email me if you have any questions about it. All right, guys, I'll see you on Monday.